Okay, class, what we're talking about is taking a look at Chapter 8. It's called Polygons and Area. The section we're going to focus on right now is 8.1, Classifying Polygons. Okay, so if we flip and take a look at the objectives page, see what the focus is today. Um, First and foremost, we're going to recall what a convex and concave polygon are. And then second, understand and apply what it means for a polygon to be equilateral, equiangular, and regular. Okay, so taking a look here at the first objective, again recalling what a convex and a concave polygon are. Um, the way I like to say it is a convex polygon has all vertices that are not punched in, if you will. And then when we talk about how does that differentiate from a concave polygons have one or more vertices that are actually punched in. So where it says take a moment and write down what you remember about convex. So a convex polygon has no vertices punched in or caved in, and a concave polygon has one or more vertices punched in, if you will. Okay, if we flip over and take a look, you got the definition. A polygon is convex if no line that contains the side of the polygon passes through the interior of the polygon. A polygon that is not convex is called concave. That's a very professional definition, if you will. The bottom line is this. If you take a look at the convex polygon on the left, you'll notice that 1, 2, 3, there's 5 vertices there. It's a convex pentagon. But if you look at the 5 points, the 5 vertices, you'll notice that none of them have been punched in, as where if you take a look at the concave polygon and you focus on this vertex right here, you will notice that that vertex has been punched in, if you will, now classifying that as a concave polygon as opposed to a convex polygon. So there's the difference there. Okay, we scroll down, take a look at example 1. It says decide whether each polygon is convex or concave. Explain your reasoning. If you look at part A, I noticed that 2 of the vertices have been punched in. Therefore, letter A, this is definitely a concave polygon. Why? Because 1 or more vertices have been punched in. Letter B, that is definitely a convex polygon because no vertices have been punched in. Okay. Again, if you flip back on a previous page, there's a geometric professional definition. I like to spin it in terms of punching in vertices, which will make it concave. No punched in vertices, convex polygon. Okay, second objective, let's understand and apply what it means for a polygon to be equilateral, equiangular, and regular. Okay. So I'm going to, if you take a look there, it says, take a moment to write down what you believe equilateral, equiangular, and regular, and what a regular polygon are, then draw a picture of each. We're not going to take the time to do that. If you want to go back and do that later, you can. Okay. The definitions are right above, but the bottom line is this. What does it mean to be equilateral? When a polygon is equilateral, we're saying that all of the segments are congruent to each other. So if you're looking at the example right here on this page, there's 1 tick mark for each segment, which indicates that all 4 segments of that quadrilateral are congruent. If you look to the right, the definition of equiangular means that all of the interior angles are congruent. Okay, that's the definition of equiangular. Then we got this idea of regular. Okay, the idea of regular is taking the idea or concept of a polygon being equilateral and equiangular and putting those together in one. For example, if you're ever in a car with someone, or you drive, or if you actually drive a car yourself, when you stop at a stop sign is actually a regular polygon. It's actually a regular octagon. Okay, there's definitely a difference between an octagon, a convex octagon, in which it has 8 sides, but they all don't have to be congruent, and the interior angles don't necessarily have to be congruent if it's an octagon. But the second we call it a regular octagon, we're talking about a stop sign. Okay, and I know you've seen stop signs many a time. So when we talk about regular polygons, maybe refer back to a stop sign. Because if you ever look at a stop sign, or next time you're driving in a car, you will notice that the stop sign, all 8 segments have the same length. So all the segments are congruent, and all the interior angles are congruent, therefore making a stop sign regular. So there's 3 examples there of regular polygons. Um, so the bottom line is polygon that's equilateral and equiangular, it's regular. Looking at example 1, it says make a decision if these polygons are equilateral, equiangular, and or regular. If you look at A, um, notice that all of the interior angles are congruent, so it is equiangular. But if you notice, all of the segments are not congruent, so it is not equilateral. And if it's not equilateral and equiangular, then it is definitely not regular. So we can only classify A as an equiangular polygon. Okay? It's actually an octagon if I'm counting the segments correctly. It's an octagon that is definitely equiangular but not equilateral. Letter B, I notice that all of the segments are congruent, so it's definitely equilateral. And then I look at each interior angle, and they each have the same amount of swoop marks, if you will, so it is also equiangular. So this pentagon, this convex pentagon that we're looking at, is actually equilateral and equiangular, and because it is both of them, we now actually classify this as a regular pentagon. Why is it regular? Because it's both equilateral and equiangular, so now it's a regular pentagon. Okay, in part C, if I counted that right, it's a heptagon. 1, 2, 3, 4, 5. There's 7 sides. It has 7 sides, so it's definitely a heptagon. And as I'm looking at this heptagon, it's definitely equilateral. And now I'm checking to see if it's actually, if the heptagon is actually equiangular. And there's not actually enough information given to decide what we know about the interior angles. But if you want to go off assumptions, which technically we shouldn't do that, obviously it appears that the interior angles are different measures. So this heptagon is only equilateral. It's not equiangular, and because it's not both, it's definitely not regular. Okay? And part A, I'm sorry, that was classified as an octagon. An octagon that was equiangular, but not equilateral. Okay, flipping over. Okay, example 2, it says the polygons are equilateral, find the perimeter of each. Well, you would have to recall how to find the perimeter around something. So if you had a fence around your house, and I asked you, how would you find the perimeter of the fence? I'm hoping that you would say, well, what I would do is find the lengths of the different sides of the fence and then add all of those lengths together, and that would be the perimeter of my fence. Correct. So perimeter means to add all of the different side lengths together. Okay, so in example 2, it says that the polygons are equilateral, so you got to remember what equilateral means. It means that all the sides are congruent to each other. So we now know that this holds true because it's equilateral. Therefore, all of these segments have to be 3 inches in length. Then once again, perimeter means find the sum or the distance around. Okay, and this is actually a convex pentagon, by the way. So the perimeter of the convex pentagon is going to be 3 plus 3 plus 3 plus 3 plus 3. But if we really think about that, there's 5 sides. We're talking about 3 times 5, which is 15 inches. So the perimeter around this convex pentagon is 15 inches in length. Now in part B, counting the sides, how many sides does it have? Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I can't remember 12. It's a 12-gon. Okay, so when it has 12 sides, number one, it's a 12-gon. Second, it's actually also concave. So properly speaking, we would call this a concave 12-gon. Why? Because one or more vertices have been punched in. Okay, so it's concave. Part A, it is actually a convex pentagon. Part A, going back, I apologize, it was convex pentagon. Okay, and letter B, we got a concave 12-gon. Okay, we got 12 sides, so the perimeter of this 12-gon is going to be 4 times 12. So the perimeter around this concave 12-gon is going to be 48 feet. 48 feet. Okay, example 3, the polygon below is regular. Find the value of the variable. Well, what does it mean for a polygon to be regular? Well, it means two things. It means it's both equilateral and equiangular. Okay, so this hexagon is a regular hexagon. This is definitely a regular because they told us so. It's a regular hexagon. It's also concave. Okay, now if it's regular, it means all the sides are congruent, but it also means all the interior angles are congruent. So it's both equilateral and equiangular. But using this notion of its equiangularness from this regular hexagon being regular, we now know that all interior angles are congruent. Therefore, that angle is congruent to that angle. If we both divide both sides by 2, we get the value of the variable. X is equal to 60. We're definitely not going to put a degree symbol there because that angle is 2 times our answer, and it's not represented just as X. So we're not going to call it X, give it a degree symbol, a label. Okay. And I think that's all we have for 8.1. Thank you very much.